Hello, everyone. Thank you very much for coming. I will be talking about the somewhat dramatically called thing, the C++ rvalue lifetime disaster. Well, you'll judge at the end whether it's really a disaster or not. So it will be about rvalues. And when C++, in C++ 0.3 or in the standard library in general, we focus very much on value semantics. We want all the containers to contain values, and whenever you put something into a container, then you copy it into that container. That's at least how it was up to C++ 0.3. Now, if that thing that you want to copy into the container is pretty heavy, is containing like memory, and it's a vector, for example, then this copying used to be quite expensive. So we avoided that in C++ 11 by the invention of rvalue references. And they allow, instead of copying, the idea is you move the object. So you scavenge the resources, you take from the vector, you take the memory with you, you leave the vector empty, and you move that memory over to another vector. Here's an example. You have a vector of vectors, and you have another vector you want to put into it, and by writing std move, you just allow that vector to be scavenged, to be its resources being taken out of the vector and moved into the new vector. And that makes it all quite a bit more efficient. Now, people soon discovered, I don't know if that was after the fact or already by design, that rvalue references are also useful for lifetime management. And in C++ 11, the std_cref wrapper that you use, for example, to pass a const ref to a std bind, that was already restricted not to bind to rvalues. Because the fear was that if you have an rvalue, something that a temporary that is created in the same statement, that if you want to wrap this into a constant reference wrapper, that it would go out of scope and leave you with a dangling reference. Now, in C++ 20, there is the big thing ranges coming upon us. And there, the importance of rvalues is even bigger, is going to be even more prevalent throughout your programming. If you're not familiar with them, that's here a statement that you would write for ranges. You take, in this case, a std vector, and with that pipe syntax, you pipe it into a filter that leaves only the even elements in that vector. And what is happening here under the hood is that this pipe operation generates a thin wrapper around the vector. It doesn't do any of the filtering. And that wrapper can be iterated over. It can be treated like a container. So you can get iterators from it, and you can iterate. And while you're iterating, the filter will skip the elements that are not passing the filter. And in order to do that, that filter object has to hold a reference to the vector. And if the vector would go out of scope, that reference would be dangling. Now, to avoid that, the C++ 20 disallows creating such filters from rvalues. So this would here not compile. The std vector is a temporary, and as soon as that statement here on the screen is done, the std vector would go out of scope and would leave you with a dangling reference. So this is not allowed. Now, before we go to the lifetime aspect to references, I want to go through a few pitfalls that you may encounter in everyday programming for rvalue references when you use them for moving. So here's a little piece of code. It does a const a, returns std move. What happens? Who thinks a move is happening? Who thinks a copy is happening? Okay. Many people have no opinion. You don't get a move because you cannot move out of const. So if you want to do that, you have to make your a non-const to move out of it. Well, here you get a move. That's more efficient than your original copy, but is that the best we can do? Why not? Copy elision. Right. So if we just skip the std move, then we get something called name return value optimization, and the copy and the move is elided altogether. The way this works is that the compiler generates that A already in the place that is reserved for the return value. So it doesn't need to move it there or copy it there. It's already there. And then the copy constructor, the move constructor, is not even called. So keep in mind, std move can make things worse. Now, what if you put a const on it? Who thinks you still get copy elision? Who thinks you don't get copy elision? Okay. Okay, there are some mentionings there. Well, you still get copy elision. It still works. It's still good. But what if you do the same thing with an if statement where you are returning one of two different A's? Well, in that case, the copy elision doesn't work. The NRVO requires that always only a single object is being returned. That makes it very easy for the compiler to say, well, that single object that's being returned, I'm going to put that into the special place that is reserved for the return value. And if you then put in the const, well, then again, you are back to a copy. So, maybe not so great. If you remove the const, you get the move. That's fine. Now, what if you access members? So there is now a structure B that contains an A. And you generate a B and you return b.ma. You may think, well, I mean, the return A figured out that A is an R value, then this should be easy, right? Well, it's not. So members are not automatically R values when they appear in such a return statement. What you can do is you can explicitly move the B. You can say, oh, the B, that's an R value. And then the member access is actually going to give you an R value, and that's going to be moved. So that's okay. You don't have to write it all the way around the MA, but and that's arguably maybe the better way to write it, because you're basically saying what you mean. You're saying, oh, my B is now going out of scope. I don't touch it anymore. And whatever access I'm doing can benefit from the fact that I'm not going to access the B anymore. That's kind of the semantic thing that you're really saying here. So what are my recommendations? I make all the return variables non-const. I know that you may sometimes get lucky and NRVO kicks in and then you can make them const, but it's a bit dangerous if you later change the code. So my recommendation is make them non-const. And there is a great warning if you're using Clang with wmove, you can get all kinds of std move warnings that point out to you if you did a pessimizing move, if you did something wrong regarding std move. Okay, let's move on to something else that is R value related. The temporary lifetime extension. Now, let's say you have an A, again, and you have a structure B that contains the A. And in this case, the MA is not public, but it's private. And it's only exposed through an accessor with const access. And you can then write something like, OK, I'm getting a B, and then I get the A from the B, and assign that to an autoconst reference. And of course, then, well, you get the reference. OK, so far so good. Now, what happens if you have another structure that has a get A, but in that case, it returns by value, not by reference? So, and you want now generic code that does the right thing, irrespective of whether you have a B or a C, whether the get A returns by value or returns by lvalue reference. Now, does this work? Can you still write autoconst ref? At first glance, it looks strange, but can you? Yes, you can, because you have what's called temporary lifetime extension. What temporary lifetime extension does is, essentially, if you are creating a value and assigning it to a reference, the compiler will help you out. It will say, OK, I will extend the lifetime of that value that you assigned to the lifetime of my reference. And the idea, and that's a feature that has been in there for a long time, and the idea is kind of cute. You can kind of always write autoconst ref or something const ref, and you kind of get the right thing. Even if you return by value, you later on change the function, it returns by value instead of by reference, everything is honky-dory, everything is safe, you still get your lifetime extension. Well, let's see. Let's say we have an A, and that A is less comparable, and we calculate the minimum of two A's and assign that to a reference. Doesn't look so different from what we had before, right? So let's see how std_min is implemented. And here, you can already see that a problem is cropping up. The min takes the t as a const reference, and it returns a t const reference. So by the time that these two values, or one of these two values, is assigned to the A, the compiler has long forgotten that that was once a value. And std_min forgets about it. And then A dangles. You may think, well, maybe that's just because std_min is stupid. And I wouldn't argue with that. So let's write a better std_min. At least this std_min only in some aspects. You can write an even better std_min. But let's start somewhere. So this std_min, this our min, the our min, instead of taking things by constref and returning a constref, just does perfect forwarding. And that's kind of what's on vogue for if you are C++11, right? You do perfect forwarding, of course. So we take these two values and the two A's, and we forward one of them to our return value. And in this case, well, LHS and RHS are all going to be the same type. They're all going to be a refref, a rvalue reference, and then our min also correctly returns an a rvalue reference. So you would say, well, the rvalueness doesn't get lost. It's returning an rvalue reference. Well, the problem is A still dangles. The temporary lifetime extension does not keep rvalue references alive. It's also more than just keeping alive, because the compiler in this situation only has a reference. And that reference isn't enough. It needs a value. So it would need to create an extra copy, and it doesn't do that. So you get a dangling A. Okay, well, before we rush to a solution to this problem, let's look at something else about temporary lifetime extension. Let's say again you have your A's that are being created, some A. It either is returning a value or is returning an lvalue reference. And you simply want to pass it through. You want to simply return whatever your sum A returned. And that's easily written in C++11. You write decl type auto foo return sum A. And then foo will return exactly the same thing as sum A return. So value for values and lvalue references for lvalue references. So far, so good. Let's do something else in between. We first take the A, and then we do some other code, or maybe inspect the A or whatever, and then we return it. Should be easy, right? So let's see. Let's try. That was my first attempt. Decl type auto foo, and then you take auto constref A, and you get temporary lifetime extension, right? It's great. And then you return the A. The problem is that this temporary lifetime extension doesn't mean that the type of A changes. It's still a const reference. It's not a value. And by the time you return it, the compiler doesn't care if there is any lifetime extension for you or not. This applies to the lifetime of that one reference A, but not to anything else, to any other reference that you now return. So you get a dangling reference. Let's try this. Decl type auto, maybe auto, it's safer. It's safe. Yeah, of course it's safer. But then you create a copy, right? The auto will always decay, and irrespective of any lifetime extension or you returning a reference or a value, this will always return a value. It's safe, but it's not efficient. What's the problem here? In my opinion, the real problem is that temporary lifetime extension is lying. You want to reason in your code about types. You want to react to different qualities of types. But the temporary lifetime extension, even if it is invoking and if it's keeping a value alive, it is saying I'm a reference. And that breaks the reasoning about the qualities of that variable. How can we improve that? I would say deprecate temporary lifetime extension. Get rid of it. We are now defining or creating types that are determined by the compiler in many places. We can actually give this A that we want to return the right type. The idea is give it a value type, let it be a value if that expression, the sum A, returns a value. And let it be a reference if that sum A returns a reference. And then we wouldn't have this problem, because then we could actually reason in the rest of the code about what kind of thing we have there. And then maybe we get the right answer. So how do we do that? Well, first of all, we need to write our little type function that when you give it an lvalue reference, it keeps it as an lvalue reference. If you give it an rvalue reference, it turns it into a type, into a value. Here's the stit decay. And now, I'm so sorry, we have to use a macro to kind of replace our assignment. And that's the best I can come up with. So you define this auto-cref macro, and it takes the type of the expression you want to assign, appends a ref, and that's important so that when you return a pure value, then you will still go into this branch here and keep it a value. And if you actually have an lvalue reference, so if you have a const ref and you append a ref, it will actually stay a const ref. So it's all good. That's reference collapsing does that for you. And yeah, and then you use that macro, and then you assign the expression at the end here. Okay. If we use that, actually, everything works. So the auto-cref, A, sum A, then A is either a value or a reference, depending on what sum A returns. And then you return the A, that same type is returned, and you're returning a value or a reference. Don't put any parentheses here. If you put parentheses there, then you are getting the type of the expression, which in case of when you're creating a value, even if you're creating a value, this is going to be a reference, and you get a dangling return. So here you want the type of the declaration, you want a type of a variable, and that's the way to write that. Now, we make this our default auto, and it works great. Maybe you think, wow, this is so strange. These guys use macros in their code. Yes, we do. But it works fine. It works, it does the right, it comes very close, or it is as good as it can get in terms of doing the right thing automatically. And so what the intention of auto-constref, of the temporary lifetime extension, is now done by this auto-cref. It doesn't work yet if you have macros, if you have lambdas inside your expression, but that's going to be fixed in C++20. It's about determining the type in an unevaluated context of a macro, of a lambda. Now, there's one choice you have to make. I told you that we made the value mutable. You can also decide you want to make the value const, because, I mean, the auto-constref you are getting is really a constant entity. You can't mutate it. So maybe you want to have the same for your value. But then you have to make the decision, and we do that case by case, whether you want to move out of that value. So, for example, when you want to return it. And in that case, then you have to use some auto-cref return, which creates a mutable value. Your choice whether you want to have that extra complexity. Okay, now let's see whether we can use that for our original problem. So if we now use our min, and we just forward the A as an rvalue reference, and we combine that with our auto-cref that we just developed, then everything is fine. Our min returns an rvalue reference, and the auto-cref correctly turns that into a value. So that's what we want. Okay, let's see. So let's see whether we can use the auto-cref for other stuff. Again, I got a structure B here, and that structure B contains a member A, and I want to get that member A, and say it's a public member. I can simply write auto-cref A, and then B, we have an R value of B. I create a temporary of B, and then get the A out of it. As we've already seen, a member access on R values gives you an R value reference, and then the auto-cref turns that into a value. So although after the statement the B goes out of scope, A still contains the value A. Okay, now, so here, this works. Okay, well, let's make this a bit different. Let's say the B, again, has the MA privately, and we write an accessor for it. And again, the same thing, auto-cref A, B, get A. Well, does that work? Unfortunately, it doesn't, because suddenly the decal type of this expression, B get A, of course, is the return value of your get A accessor, which is a const reference. And I mean, we write this all the time, right? This is just standard code that we without thinking, you would write an accessor like that. Well, if you use it the wrong way, you get dangling references. Now, it doesn't make a difference whether you use the new notation. You think that maybe when you write a const ref with an ampersand, which is a new notation, I don't know when it exactly was introduced, 14 or 17, then anything would change. No, it doesn't. It basically just means your this, in this case, is a constant reference. And that will just bind to R values. That's all fine. It will just do it. Now, the problem really is that the const ref binds to anything, including R values. And there's nothing really you can easily write that doesn't do that. That says, okay, I'm only taking constant L values. There's nothing. And it affects any accessor in the language. So there are a gazillion classes out there that have these accessors, and they are all, strictly speaking, wrong. Now, I call this R value amnesia. C++ kind of forgets about R valueness. It's like, there was an R value, that doesn't matter, I bind it to a const ref, gone. Forget about the R value. And in their internal wisdom, the people who designed this kind of knew that there's a problem, I think. Because look at this. I'm saying the conditional operator is afraid of the R value amnesia, and you can see what I mean by that. Let's say we have two functions. One returns L value references, L value const ref, and the other one an R value const ref. Now, what's the decal type of a ternary operator that takes both of them and picks one of them, and that's the type of that whole thing? Well, what's that type? If both are const refs, it's a const ref. That's what you expect. If both are const ref, the type stays a const ref. Now, what's the type of that? Who thinks it's an L value reference? Who thinks it's an R value reference? Who thinks it's something else? It is something else. It's a const. Okay? So the type of this, by the standard, is a const. So basically what they said is like, oh my God, we are in trouble here. Right? We want to, if we keep this R, we cannot make an R value reference, because usually the L value reference wouldn't bind to an R value reference. But we also cannot do it the other way around, because then we are kind of afraid that if we just assign that somewhere or use it somewhere, the pure R value, or the R value reference, would be gone, and then we'd be in trouble. So we better make a copy, and that's what they did. So they actually made the copy const, which I don't know if that's reasonable, but that's what the standard says. Now, C++20 has another facility to combine types, which is reference types in particular, which is common reference. The reason they needed that is when you have a range or a container, and that container returns something. Returns its iterator star it has a certain type. You may want to take these two containers and merge them you join them together or you merge them, and then you need, if you iterate over that, you need an iterator that is kind of the common reference of the two other iterators. The two other iterators, each of them, when you say star it, they have their own type, and you have to combine the two to form the new type of that new merged iterator that can contain both of them. And it's consistent. If you give it an a-constref and a-constref, then the result is an a-constref. And if you give it two rvalue references, the result is an rvalue reference. Now what's this? It's an lvalue reference. So the common reference really likes lvalue references. The funny thing is, if you give it an a-const, which is not that different really. I mean, we saw that when you do the forwarding, the perfect forwarding, that easily turns a value into an rvalue reference. So these two are kind of similar, except no, there generates an a, makes a copy. I don't know. So the STIT common reference embraces the rvalue amnesia. It's like, we forget about rvalues. That's fantastic. Let's do that. So what is correct here? What do we do? I categorized here the references along with their promises that they do. So they either have a short lifetime, rvalues, or a long lifetime, lvalues. Or the references are mutable, const, or they're immutable, const, or mutable. And the question is, which conversions do we actually allow here? And the current C++ does this. There's one more. So I said lifetime and mutability. There's another property that is kind of like a promise, which is the rvalue, mutable rvalue reference allows scavenging. And you cannot scavenge, for example, as an lvalue reference because this is going to have side effects. You're not supposed to. But if you have an rvalue reference, you can scavenge. So it's kind of a promise that you should also not break. So, but the current C++ reference binding clearly has arrows that go from left to right. The rvalue reference binds to a constref. The constref ref binds to a constref. So it inadvertently extends the lifetime of your references from short to long. You probably don't want to do that. To fix it, we would have to turn around some arrows. So we only go from long lifetime to short lifetime. And the guiding light here is we allow binding only if the promises get weaker. We want less lifetime, we want less mutability, and less scavengeability. You don't want something that you couldn't scavenge, like steal resources out of before, to be turned into something which says, yeah, that's fine, just take it, right? And things will break. So the takeaway is only lvalues should bind to constref, but anything may bind to const refref, which is kind of this ugly stepchild of the type system. No one really knows, well, why is there a const refref? You always just write const refref delete, maybe. That's all you do. Well, if you look at it this way, the const refref is actually your universal, I have very weak expectations kind of reference. It's so sad. I think it's so sad. I think we made it wrong. So, the question is, can we fix it? Big warning. These are ideas. They have not been implemented, very speculative. That's the best I could come up with. Okay? But if I tell you that something is wrong, I should better tell you my best ideas of how to put it right. So, of course, existing code must continue to work. You cannot break existing code, never. In C++, never. Even existing libraries, when used with new or old code, we cannot break, because the libraries are not going to change overnight, and we cannot keep people from using all these valuable libraries that are out there. I want references to use either the new rules or the old rules. So any reference is going to have a little hidden thing on it that says either new rules or old rules. And they think, oh my God, now we have two different references. This is so scary. And you cannot even see it. Well, maybe it's not quite so scary, because this reference binding only happens at the beginning of the lifetime of a reference. Once it's bound, it doesn't change anymore. So if you then inspect the type of a variable, for example, you get a truthful answer, because it's not going to behave any different either one if you have either one of the models. It doesn't matter. So we can keep the type system unchanged. So how do we do the migration now? Let's introduce a pragma. Let's say, okay, usually the old rules apply, but if I'm switching the new binding on, then the new rules apply, and then I can also switch it off again. In order to jog your imagination a little bit on where this is relevant, here are the places that I came up with where we are binding to references. Okay? So the most obvious one is the local and global variable initialization. But there's also structured binding. And of course, there are parameter lists in lambdas and also in functions. There we have declarations, and depending on whether they are framed by the pragma, that would affect their binding properties. Now, there are also members in structures, and they are either initialized as PODs or in constructors. I think it shouldn't matter. The relevant part is where's the declaration of that variable. Is it guarded with the new binding, or is it not guarded? So the a constref m_a is that would be the thing that matters. And there are lambda captures. Now, how does it exactly would work? So say you are declaring here an a, which is in constref, and then you switch on the new binding, and you declare two more, which is in constref and c in constrefref. You switch it off, and now you define b. Well, I think there's a good argument to say, well, don't do that. Okay, because the b is once defined outside of the guard, and it's declared inside, and you kind of should pick one of the two. And then the effect would be, well, as you expect, the A5 still compiles because it takes by lvalue reference, but it's not affected by the new binding rules. The B cannot be called with a 5 because you cannot bind rvalues to lvalues. But the C5 would then compile. You can bind to constrefref. I think there's no good reason not to. And the C would also bind to the const refref. So the C5 obviously binds because it's an R value, but even the L value down there, the CA, would also bind against the const refref in the parameter list of C. I thought about, okay, what kind of impact does that have on a standard library? Well, you probably want a feature test macro. You probably want to be able to check whether this new binding behavior is enabled or not. Maybe also, in addition to knowing whether you can actually, whether the compiler supports it, you also want to know, am I inside such a guard? Functions can be implemented equivalently, mainly by just replacing the constref parameters with constrefref parameters. It may be a little bit of a mind warp that you would see all these constrefrefs throughout the code, but I don't think it would be so bad. And we would have to rewrite, we would have to have an old version and a new version of std common reference. I went through the type traits, what's defined there, and whether there are any more that are reasonably affected. I couldn't find any, so std common reference is really what's affected. Common type would be okay. That's always generating a type. It's always decaying. Okay. But until we have all that stuff, we have to have some mitigations to the problem. We have to do something just practical. I already showed you the auto cref that replaces the temporary lifetime extension. And whenever you're writing a constref accessor, well, you should probably delete the rvalue accessor. Why shouldn't you implement it? Well, the question is a little bit, how would you implement it? If you say you implement it by returning a value, which is the safe choice. The problem is, maybe at the point where you need that overload, you could actually scavenge. You want to at least consider whether that's a possibility. You could say, okay, well, why not then implement an rvalue accessor? Well, the problem is the MA here is private, and it is not clear whether that's a valid operation to just scavenge from the internal MA. You can't just do this blindly. So the safe choice is just delete the accessor, and if you happen to need it, the compiler is going to point it out to you, and then you can still make an informed choice. Now, here's the better implementation for common reference. This one is actually implemented through the regular std common reference right here. You first calculate the std common reference, and then if that std common reference happens to be an lvalue reference, then you have to check, well, is that lvalue reference here okay? And you do that by checking, well, is any one of my inputs, or is any one of these an rvalue reference? And if it is, then we just turn the lvalue reference into an rvalue reference, otherwise we leave it alone. And with that, we can actually get rid of that rvalue, the rvalue amnesia, C++ rvalue amnesia fear of the ternary operator. So if you have a decal type false R with rvalue and lvalue, I already said that the type is going to be a const, and C++ is going to force a copy. Well, you could use the new common reference to cast both arguments to the same type, to the same common reference, and then apply the ternary operator. And you can encapsulate it into a macro so that you have one that doesn't always force a copy. Okay, that brings me to the end. And here it is again. It's a const ref now, and you don't get an immediate copy. So that brings me to the end. Thank you very much. And here's the summary. So the big mistake was that const ref should have never bound to rvalues, I think. And fixing C++ may be possible, but I think the only way that you would have a minute chance to get that through the standard committee would be that we have an implementation on Clang, and that implementation has been tried out on a really large code base, and it's documented how much of an effort it was to actually do the changes. And if that is kind of catching on virally, that kind of people do that, then maybe we have a chance to say, okay, maybe we can change the standard. And until then, we just have our mitigations that we try to protect us from these kind of problems. Thank you very much.
We still have 20 minutes for questions and answers. So if you have a question, please raise your hand. I'll come up.
Thank you for your talk. I have a question about, have you any experience in performance difference between binding const ref or const ref in your code? I think it's no difference.
I mean, the generated code at the end should be the same. I mean, I think bitwise there should be no difference.
And if I understood that these tricks are only for best practice in readable and usable, not about performance, yes?
Correct, yeah.
Okay.
We're arguing about protection from semantic mistakes you make in the code.
Okay, thank you very much.
More questions?
Well, suppose the situation when we have a function which gets a container, a reference to a container, a const reference, and it has to iterate that container, for example, using a range-based loop. And this is a generic code, and so there are times we are calling that functions with a container returning values, and the other time we are calling that function with a container whose iterator the reference as const references.
Okay, sometimes it's a value and sometimes a const.
How do we declare the variable in the range-based loop if it doesn't bind, if double reference doesn't bind to const reference, how we do that? Will it work?
So I don't. You probably can't. Good point. I feel that the range-based for loop. Again, this is heavily influenced by my personal opinions. I think the range-based for loop is bad. Don't use it, ever. And here's the reason why. The range-based for loop at the end is a raw loop. And very often, your intent is much better expressed using an algorithm, especially now with the C++20 ranges coming in, where you can put the range into algorithms. You can write an accumulate, you can write an any off or an all off or anything of these kind of things. And I disallow, in our code, I disallow range-based for loops because even if that's what you mean, even if that's what you want, is a for, then once the for loop is written, people have momentum. It tends to stay that way. So even if later on you discover, well, maybe it's better to put an algorithm there, it's already in a form that favors it staying a for loop. If instead you use for each with a lambda, you already have a lambda. And then it's much, the jump you have to do in order to do, instead of a for each, to do an accumulate, because that's better suited to what you want to do, or an any off or something, is much smaller. So before you have that for loop, and you test some condition, and then you say break, or you say, oh yeah, result, it's true, break. Well, to see, okay, this is an any off actually, and I should rewrite it, requires you to rewrite the whole thing as a lambda, which I think you should do it right from the start. So we only use for each. We don't use the range-based for loop.
Hello. Is there any disadvantages of enabling pessimizing move flag in some huge projects?
Say again?
Is there any disadvantages of enabling pessimizing move flag?
No. I mean, yeah, you should, pessimizing moves, you should.
You recommend it?
Yeah, enable the warning and get rid of them.
Thank you.
Hello. The question is there such thing as a perfect reference that usually like in templates t ref, and in that case it semantically looks like a rvalue reference, but with your suggested new binding rules, it will work differently. So t ref will accept any reference and any value, because it will basically become either r value or l value, but like normal, a ref will not bind to t, will not bind to l value. So it will like kind of look differently, don't you think?
I'm not quite sure. So when you use a universal reference, then the binding would still happen the same way. I mean, there's no conversion happening here. I mean, that's precisely that it's basically adapting to the type that you are passing. So if whatever reference you would pass, that would be the reference of the type you're getting. I think that would be unaffected by changing all the binding.
Yes, but that's exactly like what I'm asking. So it will be different, like T ref will behave differently from A ref in that case.
Correct, but that's already, I mean, that's already the case today. So I don't think there's a, yes, but it's already like that now, so we'll stay that way.
More questions? Okay.
Can you explain once more time why we should delete ref member accessor?
Yes. The problem is if you're creating a temporary that will go out of scope by the end of the statement, and then you create a temporary either by directly calling the constructor or by something that returns the value, and you say dot your accessor. Then what you are returning there is a const reference. Now, if your code does any reasoning about what having a const reference means, then you may accidentally assume that this const ref has a long lifetime. I mean, for example, say that Accessor returns a container, and that container is something you are sticking into a filter expression of the range library, the new C++ range facility. Now that expression will happily compile. It will say, yeah, it's an lvalue reference, everything is fine, and you get a dangling reference. So you're really trying to guard against accidentally getting dangling references because you're calling const ref functions on temporaries.
More questions?
But I can define ref member accessor as returning value or
yes,
member my member.
Yes, you can. So you can define your aref accessor by, for example, returning an aref of the member. That would basically simulate exactly what's happening when you are doing the access on a public member function, on a public member. And you can do that. I'm just saying that don't do that by default, because unlike public members, a private member is not expected to be changed at will, to be turned into an invalid state just by the calling of an accessor. If you know about your class, that's fine, then by all means do it. Just if you are basically just as a hard and fast rule what to do, if you want to put this into a macro, for example, there I would just for safety I would just delete the const ref. And because anything you do may be wrong. If you're returning a value that's safe but potentially inefficient, but if you're returning a ref, then that's potentially wrong because your class cannot deal with it. Your class is not designed for this internal state to be simply scavenged away.
Thank you for your talk. Kind of philosophical question about the whole reduc. When the standard was broken, actually, was it C++ 11 or later? And can we speculate about what should have done differently to?
Nothing. I mean, I think they were very much aware of the problem. The situation was that, of course, in C++ 0.3 already, const ref was binding to rvalues because there was no distinction between rvalues and lvalues. That distinction was never made. So we had tons of code that actually just took the const ref and had rvalues binding to const ref. I think what is increasingly happening, and you can see that in the C++ 20 range, which is why this topic may become more relevant, is that people kind of are more aware of lifetime issues. They're more aware of maybe the language should actually help us be aware of lifetime and doing the right thing in terms of lifetime. And we're trying to do that using rvalue references. But at the same time, the language contains rules which break that assumption. And that's kind of sad. The only thing to do is, something like I proposed, you have to change the language, and that's incredibly hard. And yeah, so we are here for a good reason. It's not like someone was completely stupid, no, but still it's wrong.
So, is there any proposals to fix
No.
this actually?
No, I think, and if you ask me, the way to address this would not be to make a proposal. The way to address this would make implementation in Clang, have it hopefully go into the trunk of Clang and be distributed throughout, so that people can play with it and people can lose their fear about change, making such a big change. My feeling is the change is not going to be so terrible, because most places it's going to be you replace constref with constrefref and you're good. And because we are not the places where no, I think I would leave it at that. Yeah.
Okay, thank you.
Thank you for talk. Could you clarify a bit what is the best practice you recommend for using this pragma during the code-based refactoring?
Well, I mean, the idea would be that you use it everywhere. I mean, you want to migrate your code at the end. At the end, in an ideal world, we would say, okay, there's still these somewhere some old code that uses the old style, but kind of I think there's also in JavaScript you always write strict at the beginning, and that would be kind of like, okay, the first thing you do is you just do the new binding rules. Yeah, in an ideal world.
Thanks.
Questions? More?
Back to your slide where you were creating a view on top of a Rvalue reference of a container. And you mentioned that it's not going to work, right?
You mean the very beginning?
Yeah.
Here.
Yeah, so it doesn't compile, or it will compile, but it just will crash.
Does not compile.
Doesn't compile.
Doesn't compile.
And why
compiler will protect you.
Yeah. Why wouldn't it be possible to actually capture this container into this lightweight view and just keep it for the lifetime of the view? Yeah.
Yes, good question. And I think there was a discussion whether to do that when C++20 ranges were introduced, and we actually advocated to do exactly that. We do it in our own internal range library, and it works great. But the standard committee sees it this way. Now, they have a very strong distinction between views and containers. Views are lightweight, or are supposed to be lightweight objects. You can copy them around at will, and they just hold references to their objects. And the other group are containers, where the containers own their objects. And these two, understandably, have very different copy semantics. So one does a shallow copy and one does a deep copy. One has value semantics and the other one has reference semantics. And they were a bit, I think they were a bit reluctant to, with the same kind of expression, create, depending on the circumstances, two different kinds of objects, which would have two different semantics. This was considered scary. Now, we tried it, we have it in our code base, and it works just fine. The reason, I think, is that it is very rare that you actually copy ranges around. Just like you usually don't copy vectors a whole lot because it's just expensive. You also really don't copy ranges. And so this semantic difference you have to be aware of, but it has never bitten us, and we've written 1 million lines of code with our range library. It's never been a problem. So just empirically, I think that's a very good suggestion. The standard committee has a different opinion.
Does it mean that if I have a function that returns a container,
you have a huge problem?
Yeah, it's not going to compile. So, if I try to make a view.
So the real problem comes in if you have a function that is supposed to return a lazily filtered container. So you want to return a container, and you want to attach some adapters to it. Say you have some generic code where sometimes it's supposed to be a container, and sometimes it's a filtered container. And you want to do the filtering lazily because you don't really know how many of these things you actually need. So you want to do the filtering lazily. Now, if you create the container and then you want to attach that filter to it and return that whole object, I don't know of any good way to do that in C++20 because you only have a reference, and that reference is going to dangle, and you cannot package these two things together, the filter and the container, and move it out of the function and still have maintain that reference to the container. So it's I think that's for me that's a good argument to actually in that case aggregate the container into the filter object.
I think I know one way you can create a shared pointer. I mean, you can allocate a vector, create a shared pointer, capture it, and just
You can allocate everything on the heap, and then that's kind of the way out. But it's not very satisfying because it's inefficient.
Question: is it different in boost ranges right now, or?
Boost ranges also boost ranges are much more primitive. They basically, all the adapters are just iterators. They are just expressed as iterators. So you would have the same problem. It's the way they're implemented is that there's not the adapter object holds a reference to the container, but instead the iterator has an iterator of the base range. And that iterator would also dangle, so you'd have exactly the same problem without the safety of C++20. It wouldn't call it out to you, it would just dangle.
Okay, thank you very much.
Well, there is, I have maybe not a question, but I'd like to share a crazy idea. You already said JavaScript today, right? There are objects and there are no dangling references at all because the virtual machine takes care of the lifetimes of the object references, right? And in C++, it feels like all those rvalue references came into play as a mean to reflect the fact that C++ actually doesn't care about the lifetimes of object references. Well, how do you feel? Could it be possible to develop the C++ in the way more like such that the compiler would be able to take care of the correct lifetime of object references? It is totally crazy idea.
Well, I mean, I think I'm by no means an expert on that, but first of all, I mean, all these languages that only have references, they are not in the same league in terms of performance, and I also very much like the deterministic destruction of C++. That's very close to my heart. I mean, there are attempts in Rust to do exactly that, to have a system that manages lifetime for you, and where you can have the efficiency and the value semantics, but at the same time have safe lifetime. And I haven't tried it, to be honest. I hear sometimes that it's a bit cumbersome to use, and some other people like it, and I don't know. But I think getting that into the standard C++ standard is way beyond anything.
All right. If there are more questions left, then you can join Arno in the discussion zone number 2. He will be there shortly. Thank you. Let's thank Arno.
Thank you very much.